We like to think that by now we have explored even the most remote corners of our planet. But this is not true. The deepest parts of underwater caves are unreachable for humans, so their exploration can only be done with specially designed tools. Researching Hranice Abyss, the deepest underwater cave on Earth, is one of the most demanding challenges. At the cave, close to Brno in the Czech Republic, intense preparation is underway. The leader of the research expedition, Michal Guba, is trying to keep control on the mass of ropes, strings, straps and cables. The tiny lake, which marks the entrance of the underwater passage, is surrounded by 70-meter-high steep rock walls. Not an easy place to carry down this huge box, and all the things necessary to operate the device in it. Fortunately, over the decades of research, a cable line has been installed, and the team is also well experienced. But what is hiding in the box? The best device for the task one can have. Meet the UX-1 Neo, one of the most sophisticated underwater robots in the world. The expedition is organized by the Czech Speleological Society, and all participants, including engineers, coders, geologists and cavers, joined forces for one reason: to explore and map the deepest section of the cave. To achieve that, they have to dive deeper than 404 meters, and by doing so, set a new world record. The robot and the abyss. The Hranice Abyss expedition is rather ambitious, but by no means a hopeless idea. The development of the robot started years ago by numerous research institutions from all over Europe with Hungarian coordination. Thanks to the clever design, the assembly of the UX-1 Neo looks like child's play, yet in reality it takes weeks. When all the parts are in place, the robot gets its special cover. These hard foam shields are not just protecting the sensitive instruments, but also ensure neutral buoyancy for hundreds of meters of depth. The assembly and the first test are carried out at the laboratory of Inestec in Porto. This pool is made exclusively to test underwater robots in a secure environment. This is a safe place to find out the potential problems and fix them. Soon, the robot has to prove its capabilities in places where the stakes are much higher. Under the lush pastures of Peak District, England, hides a special mine. In the 18th century, the raw material produced by the Egton mines was crucial for British superiority at sea. The copper from here protected the hulls of the Navy's ships. Since the deepest parts of the mine are now underwater and we don't have detailed documentation of what is down there, historians have to use unconventional methods in order to find out how mining was done here. The UX-1 Neo is designed to explore flooded mines, more precisely to gather information on the raw material potential of abandoned and flooded mines. That doesn't necessarily mean it can't be used for historical research, especially in the case of an important industrial heritage. The former mine office now transforms into a state-of-the-art control room. The visualization of the data recorded by various sensors and the navigation require numerous workstations with even more displays. The robot is equipped with sonars of different kinds, video cameras, and a special laser scanner system called SLS, all in order to get precise information on the physical environment. On the monitors, we can see the mapped section, and in it, the position of the robot in real time. The SLS projects spectacular laser planes on the walls, and by recording and analyzing them, we can get the 3D model of the passage with millimeter precision. We can also use the images of the video cameras to create realistic models by using the method called photogrammetry. But there are things which are invisible even for these devices. It looks like the robot got entangled in a fishing line, which was probably used for measuring depth some time ago. Luckily, old fishing lines are not really durable. Therefore, the chief engineer of the robot, Carlos Almeida, decides to take action and saves the trapped UX-1 Neo with a dedicated tug on the umbilical. On the surface, it turns out that the situation is more severe than they thought, as one thruster had wound up several meters of line and became blocked. Thanks to the modularity, it is relatively easy to dismantle, repair, and test each part. So, after a short technical break, the dive can be resumed. Egton is a relatively simple site, and success was easily achieved. But let's see how the robot can cope with a deeper and more complicated modern mine.
Any unattended articles are likely to be removed without warning.
Cornwall was once a flourishing mining area, but by now all of its mines are closed. Without mining, it has become one of the poorest parts of the United Kingdom, with a high rate of unemployment and strong nostalgia for the good old days. The South Crofty tin mine was closed due to the low tin prices. But according to the geological assessments, great amount of tin can still be found here. Tin-rich veins are clearly visible in the tunnels. As the market price of tin increased considerably in the last couple of years, it would be worth reopening the mine. It is not all that easy. Precise information on the state of the flooded parts is needed to plan the dewatering. Perfectly fitting task both for the robot and the team. The harsh conditions pose a challenge for everyone. A real mine can be a rather unpleasant place. The air quality has to be monitored constantly, and wearing waterproof clothes is strongly recommended. Nevertheless, the real difficulties start in the water. The widest part of the robot is 70 centimeters, and the most spacious aperture between beams in the shaft is only 90 centimeters wide. The dive has to be done using this void all the way down to 280 meters. As if that were not enough, it turns out that the visibility is zero. There is no other option for navigation but to rely on the images produced by the horizontal and vertical scanning sonars and the frontal high-resolution multi-beam sonar. Thanks to the concerted imaging of the different devices, the robot reaches the target area in safety, and the gathered data looks sufficient to plan the dewatering. The clock is ticking. There is only a couple of weeks left until the Hranice Abyss expedition. It is time to speed up. The team transfers the robot to Budapest, which is the next location of the preparation. The several kilometer-long Cabana mine is partially flooded. The clear water and the complicated passage structure represent an appropriate site for practice. Mining equipment from the past is perfect for testing the abilities of the laser scanner. The multi-level chambers and tunnels can be used to fine-tune the navigation and validate the autonomous distance-keeping and object avoidance systems. The UX-1 Neo doesn't need permanent control. It is enough to mark the next waypoint on the map it makes. It can navigate autonomously from the starting position to the next waypoint while keeping a safe distance from walls and objects. Thanks to the satellites providing GPS data, we can easily determine our position anywhere on Earth. All we need is the right device. If we have some kind of a map and our position on it, navigation cannot be a problem. Underground, like in the Molnar János cave in Budapest, the situation is entirely different. GPS doesn't work here, as the signals from satellites cannot be received. The navigation has to rely on something else. First, we need a starting point with known coordinates and orientation. In our case, it is a chessboard. The UX-1 Neo automatically recognizes the checkered pattern as a calibration point. During the dive, the robot relates both its own location and the mapped environment to this starting point. Sounds easy, but in fact it represents a great challenge for engineers and programmers alike. The robot's own position is determined by an optical gyroscope, which registers the direction and the intensity of movements. In addition, the so-called DVL senses the movements of the environment, like water flow, and provides correctional data. For mapping, the robot is equipped with 2 perpendicularly mounted scanning sonars, a high-resolution multi-beam sonar, 6 SLSs, and 6 video cameras. The exceptionally good maneuverability is achieved by 8 thrusters. But there is also a buoyancy adjustment system and a pendulum, which can be used to change the robot's center of gravity. All squeezed into a sphere only 70 centimeters in diameter. The Molnar János cave has a complicated maze-like layout, which means if the robot handles this place, it is quite possible that it won't have any problems in the Hranice Abyss either. Diving in zigzag passages can also answer the question of how many twists and turns can be made with the optical cable which connects the robot to the control room. Caves develop along the cracks and fissures of the bedrock. By doing structural analysis on the cave wall models, it is possible to point out the fractures and fault planes that determine the directions of the passage development. The models created by the robot are not just spectacular, but due to their precision, they can help to understand the geological processes that led to the formation of a cave. If we could make a similar model of the Hranice Abyss, we might get closer to understanding how and why there, the deepest underwater cave in the world, was formed. Around the Hranice Abyss, thermal waters reach the surface, and they are responsible for the existence of many particular geological phenomena. The Bachva River runs in the nearby valley, and due to the carbon dioxide content of thermal waters, it is bubbling heavily. On the other side of the valley, there is a popular drinking fountain with natural sparkling water. By climbing a little bit higher, we can reach the entrance of the Zbrashov Aragonite show cave. The spectacular formations of the cave are eye-catching. The glistening crystals covering the walls are not just of aesthetic value, but in the eyes of an expert, they are evidences of the presence of thermal waters. In this area, the thermal waters are always accompanied by carbon dioxide, which forms an invisible but deadly layer on the bottom of the passages. If we lower down a lantern on a line, the flame dies when it reaches the level where there is not enough oxygen for the burning because of the elevated carbon dioxide content. The formation of the limestone caves can happen in two ways. Either downward flowing surface waters or the upwelling thermal waters are responsible for the cave genesis. There are two theories regarding the formation of the Hranice Abyss. According to some, this unique cave was shaped by the upwelling acidic thermal waters, while others think that the valley used to be much deeper and the surface waters running towards the valley carved the shaft. We still don't know which theory holds the truth, but it's also possible that the combination of the two is the right answer. After decades of research, we still don't know some basic information. For instance, how deep is the cave really? Or what precisely does it look like? Humans can only access the cave to a certain depth. Regarding the lowest known section between the depths of 270 and 404 meters, we can only rely on a single video footage made by an ROV. No wonder everybody is enthusiastically assisting the first dive of the UX-1 Neo. The primary aim of the expedition is to create a precise map of the upper 200-meter section. Doesn't sound too daring, but if achieved, it will be a big step in the exploration of the cave. A milestone which has been dreamed about for ages. The robot is ready, and the essential chessboard is also in place. A final system check, and the dive can start. If all goes well, the whole trip should not last for more than 2 to 3 hours. During this time, the UX-1 Neo is capable to complete the work that would take hundreds of underwater hours for divers. Slowly, the 3D model of the upper part starts to appear on the monitors. The targeted 200 meters was achieved right in the first dive. Nothing else left than to reach the surface in safety. The red alert sign on one of the monitors is indicating leakage. This is not necessarily a big issue, but a couple of seconds later, all the connections with the robot are lost. Nobody knows what could have happened. Everybody is just guessing. The joyful waiting turns into anxious preparation in the blink of an eye. Once again, humans take the stage. The robot engineers hand over the leading role to the cave divers. Petr Hrbejk and Michal Guba sign up for the task. If the optical cable got entangled or the robot has filled with water, they might find themselves in a really hard situation. Diving to this depth requires careful planning. Not knowing what is waiting for them, they expect the worst. If a lot of time is needed to resolve the situation down there, they can only surface after long hours of decompression stops. Fortunately, pretty soon promising movements can be felt on the cable. In less than an hour, the robot and the divers reappear in the lake. Still, no one knows how bad the damage is, yet it is a cheerful moment. They could manage to map the upper 200 meters, and the robot is back on the surface. Norbert Zazon, the coordinator of the development, and the divers are in an elevated mood for a good reason. But there is no time to waste on celebration. The damage assessment has already begun. The most important question is whether the main computer got wet or not. This would instantly mean the end of the expedition. The soul of the robot is then immediately sent up to the camp to be disassembled in the cleanest possible environment. The engineers think that something must have happened to the optical cable as well. And they turn out to be right. There is a broken fitting in the cable reel.
Then twisted and broke the cable.
Nevertheless, the whole robot needs scrutinizing. It is going to be a long, long night. In the camp, everybody is coping with the situation in a different way. Some are soldering sensors, some are analyzing data, while others, who can't really make themselves useful now, are pondering about chances. One thing is for sure. Even if the expedition is over, the mapping of the upper part of the Hranice Abyss is a success. This remarkable achievement cannot be taken away from the team. Soon enough, it turns out that the computer is not severely damaged, and the cable reel can also be repaired. Just a matter of a little fixing here and there, and they can carry on. Of course, there are people who cannot afford the luxury of celebrating. The development of the water parameter unit is a never-ending story. It has to work faultlessly by tomorrow morning. Or maybe not. Heavy rain arrived over the night, which has transformed the slope leading to the cave and the whole campsite into a muddy swamp. Under these circumstances, no serious action can be authorized. There is no safe way to approach the lake. Even going to the village for supplies calls for major international collaboration. But nothing can stop the team. As soon as the rain gets calmer, they are stumbling down to the platform to prepare the robot for the next dive. Getting down is not the only source of thrill. Out of superstition, no one mentions it, but they all know that if they can safely go through the dangerous squeeze called Mikado at 200 meters, they have a fairly good chance of reaching greater depths than anybody ever before. That would obviously also mean a new world record. During the preparation, the sun starts to shine once again. Not that it has any relevance in the cave, but it certainly puts everybody in a better mood. The release of the robot from the lowering line marks the beginning of the dive. In a sense, it is a ritual moment. For this dive, not by chance, it is carried out by the chief engineer of the robot, Carlos Almeida. On the platform and in the control tent, almost 40 people are cheering for success. Counting from the start of the research, we are talking about hundreds of people working for decades to make this possible. The UX-1 Neo has accomplished several missions. Everybody hopes that this time it won't be any different. The optical cable, the only connection with the surface, slides smoothly down to the depths. This section is familiar to the robot, therefore no one is expecting any surprises. The coordinator of the dive, Alfredo Martins, is already getting ready for the dangerous squeeze at 200 meters. The Mikado is the key to the deeper parts, but according to eyewitnesses and video footages, the path through this section is extremely tricky because the fallen and sunken tree trunks tend to get stuck here, blocking the way. It is obvious on the monitors that the shaft is getting narrower, and soon the trunks presenting entanglement hazard are starting to appear. The Mikado almost turned out to be fatal for a robot which was here last time. But the UX-1 doesn't have to rely only on camera images. Therefore, it can maintain safe distances from the walls, and its maneuverability is also exceptional. Despite the expectations, the navigation through the squeeze is going surprisingly well. Moreover, the progress and the mapping in the following, wider section is so smooth that the world record depth of 404 meters is passed almost unnoticed. Nothing obstructs the diving to further depths. But a safe limit has to be set, as the robot is designed for a maximum depth of 500 meters. A quick decision is needed. Although the temptation is inevitable, they decide not to go deeper than 450 meters. So this depth is going to be the new world record. And while it would be nice to linger here for a while staring at the unknown darkness, we are still only halfway. The robot needs to come back as well. The model of the whole cave is undoubtedly impressive. But on the other hand, it also shows that the surface is really far away. The cable is coming up nicely. With every centimeter and every meter, the pressure is dropping, both literally and metaphorically. As the robot passes the Mikado, everybody is relieved. From now on, nothing fatal can happen. And it doesn't. As the release from the lifting rope marks the start of the dive, the hooking back marks the end of it. The expedition was successful from every angle. But the question remains unanswered. How deep is actually the Hranice Abyss? This mission is not even over yet. But everybody is already thinking about how and when they can get closer to the answer. With only a couple of adjustments, the robot is soon going to be able to go down to 1500 meters, so there is a good chance to continue the research. The planning and daydreaming soon turns into celebration. The 3D model is ready, and a world record is a world record.
Cheers!